Alrighty, so we're group Dolce Codice, and in this slides we're going to be focusing on the concrete architecture and how we developed the concrete architecture coming from the conceptual architecture. Our member contribution, we have five right now. So we've got Fahim, Josh, Aziz, Ethan, and Sam. So for Fahim, he worked on the introduction, the abstract conceptual architecture, the derivation process, navigates, and he was a leader of our group. And then we've got Josh, who worked a lot on the use cases and did a great job on it. And you got me, who worked on the cockpit and instrument, autopilot, RTI manager, airports, stuff like that. And then we got Ethan, who worked on the FDM subsystem and conclusion, and he's a presenter, and I'm also a presenter. And then we got Sam, worked also on the AI model and the ATC scenery and environment and multiplayer. So let me give you a brief introduction and overview. So the main concept of our report and slides were to update the conceptual architecture and see how it works with the concrete architecture, and to drive the process out of the conceptual architecture to make it into the actual concrete architecture. And then we also worked on different subsystems and how they could interact with each other, and we focused a lot on the use cases and how, like, under different cases how it will be used. And we also had a lesson learned and what we learned and what we concluded out of the report. So for the conceptual architecture updates, we saw a lot of the feedback saying that we need to uh, add more client modules. So that's what we did. We focused more on having more client modules like the autopilot and uh, navigates. We already had the GUI render, but we added more and we saw how they could interact with one another. So we focused a lot on making them, and we also focused on seeing how the server can um, interact with both the database and the client modules. Okay, so for the derivation process, we mainly focused on analyzing the source code that we had and organized the directories, and we used an understanding tools to make the graphs that we see over here. And we also generated a dependency diagram, and as I said, that's where the diagram is. It's basically it shows how each and every server or every component is dependent on another one, and how they interact with one another. Yeah, so for the top level architecture, we focused a lot on giving the best user experience in terms of making sure that the user is able to interact with the simulation and be able to make it as realistic as possible so they can actually understand what happens when you're actually um, driving an airplane, or whether you are in the airport or whether you are taking off or landing into the airport. So we focused on the ATC and how it works and how it controls the traffic within the airport. The sound system. So the sound system, we found out that there's a lot of sounds that's going on within the airport, and the pilot has to know how to understand which different sounds they have to look for. And also the multiplayer. So we saw that the multiplayer is a huge part where it's collaboration, and you have to make sure that you understand how to collaborate with team members. Also the autopilot and how the user can interact with the autopilot, what the autopilot can do and what it cannot do, and how the user can actually maintain it and make sure that they can control it. And for the cockpit, it's basically the it's like gives the experience on how different airplanes have different cockpit and instruments and different keys, and how they can actually understand what's going on within their driving skills.
The Flight Dynamic Model (FDM) serves as the cornerstone of the flight gear simulation, modeling how aircraft respond to a bunch of factors including design, aerodynamics, environmental conditions, and user inputs. We decided there were 5 key components that the FDM interacts with, the first being weather and environment simulations. These components supply the FDM with dynamic real-world atmospheric conditions, enabling realistic flight behavior under varying weather scenarios. The second is the aircraft design component. This element provides detailed specifications for each aircraft model, allowing the FDM to accurately simulate flight physics and dynamics. Third is the user control response. This integrates pilot inputs into the simulation, adjusting the flight dynamics in real time to reflect changes in the control system. And the fourth is the viewer renderer component. This renders the simulation for the user, offering a visual representation of the flight based on the calculated dynamics. And all of this goes to the RTI manager. Transitioning from the conceptual to the concrete, this slide shows the concrete architecture of the FDM, which includes many other subsystems we might have missed. The subsystems that the FDM actually interacts with are the environment and scenery, the AI model, the instrumentation, the multiplayer, the aircraft, the GUI, the main, the model, and the network. And then on the diagram on the right, you can see the boxes that are outlined in red are the subsystems we missed and were added, and the red arrows are added dependencies as well. Let's talk about the divergences. Unexpected dependencies such as the bidirectional interaction between AI model and FDM ensure that all entities within the simulation adhere to consistent physical laws, enhancing realism. Similarly, the network and FDM exchange is crucial for real-time data sharing in multiplayer modes, maintaining synchronization across diverse sessions. The instrumentation's reliance on FDM for accurate cockpit readings alongside the FDM's influence on the GUI and model subsystems for visual interactive elements showcase the depth of integration required for a comprehensive simulation. These interactions are completely by subsystems like AI model, which controls non-player entities, and multiplayer, ensuring fluid dynamics across networked environments. Each subsystem, from model loading and animation to GUI data presentation, contributes to a seamless flight simulation experience. In essence, these unexpected dependencies and subsystems form the backbone of FlightGear's FDM. For our first use case, we chose turning on the autopilot. The autopilot is a feature designed to regulate the plane speed and altitude at a constant state when on. The diagram shows how the RTI communicates the user's actions to the systems involved and how these systems talk amongst each other. Overall, the autopilot feature is primarily run through the autopilot subsystem with the relevant data from supporting subsystems. You can see the sequence diagram on the right as well. For our second use case, we chose receiving data from a network server. While in multiplayer mode, the multiplayer subsystem is in a state primed to exchange data with the network. The diagram shows how the multiplayer subsystem moderates the data received from the network and readies the user's side data to send back. Overall, this is a walkthrough of one instance of data exchange with a network. And again, the sequence diagram is right on the right. Lastly, lessons learned. Throughout our analysis of the FlightGear systems, we found Understand to be a helpful tool. However, not all of its most useful features were not as obvious as they now seem. These features were instrumental in this report both for exploring and understanding the code of FlightGear. As well, we had initially begun construction of non-understand diagrams through the program paint.net, as was done with our previous report. This application turned out to be slow and time-consuming when it came down to producing these types of diagrams. We eventually were made aware of and switched to Draw.io, a browser-based software that was much more effective than Paint.net. Therefore, moving forward, we feel it would be an effective use of time at the start of the next assignment to actively look into both our current application as well as possible alternatives in order to find more effective methods for producing our report.